Hello, everybody. Happy Tuesday. Thanks for coming to class today. Like I posted on our Google Classroom, I will be out. I'll come back on Thursday. I'm headed downstate to attend the services for my father-in-law who passed away last week. Anyways, while I'm gone, we are going to continue to learn as much as possible. We cannot slow down. So you are responsible for the lessons today and tomorrow that I will give in class. Make sure you ask Mr. Nagel for help when he comes time to practice. He knows his chem stuff. All right, here we go. We're going to continue on in our current little unit that we've been working on, which is how to classify and predict the products of different types of chemical reactions. I'm going to start with a quick review, and then we'll teach you one new reaction type, and then you'll work on a formative practice. All right, here we go. So to start off for review, it's going to be important to remember the 7 diatomic, or di means 2, the 7 2-atom elements. These are elements that are super reactive, and you wouldn't just find one atom of them alone in nature in an unbonded state. So like you don't just find oxygen, one atom of it floating around. It's always bonded to at least itself another oxygen. It's always O2 when you represent it as a reactant or product in a chemical reaction. Okay, so the other thing I want to review quickly is charges of ions. We're going to need to write ultimately the entire reaction equation, the reactants, products, using the names of the reactants and products. Basically, we're going to have to remember how to do formula writing. So let's just review. Everybody here in group 1 has 1 valence electron. They would form an ion with a +1 charge. Everybody in group 2 has 2 valence electrons. They would form an ion with a +3 charge. Remember, the transition elements, groups 3 through 12, they can form different charges depending on the atom that they bond with. So the charge of these elements is given in the name in Roman numeral form. So like if it's like iron Roman numeral 3 chloride, the point of the Roman numeral 3 in the name is to tell you when you go to write the formula for iron 3 chloride, you give that iron the +3 charge. It doesn't mean there's necessarily 3 irons, but that's the charge you use when you write your formulas. So +1, +2, skip the middle. It'll be given to you in the name. Group 13, they have 3 valence, so they form ions with a +3. Group 14, we said plus or -4. It depends on what these elements bond with. Nitrogen, though, in group 15, phosphorus, arsenic, all the way down, they have 5 valence, so they gain 3 to get to the stable 8 when they bond, so -3. Everybody here has 6 valence. They gain 2 when they bond, -2. And in group 17, they have 7 out of the 8 valence. They gain 1 more to achieve stability. Thus, they form ions with a -1 charge. So group 18, they're the noble gases. They're stable. They don't typically bond. That means they typically don't form charged ions. All right, real quick review. I already taught you synthesis and decomposition. We haven't practiced it yet, but we're going to do that later. But let me just review quickly, since it's been a week, what to look for in a synthesis versus a decomposition reaction. If you synthesize something, you make something. And basically the synthesis reactions that we're going to see are going to follow a 2-to-1 format. 2 simpler substances will combine to make one single product. So you make one single substance as the result of a synthesis, sometimes called a combination reaction. So there's simpler ones, 2 elements like hydrogen and oxygen combine to make one single product like water. You can have more complex ones where 2 compounds combine to make a more complex compound like carbon and water make that's a carbonic acid. It's like what's found in soda. Okay, so this is an example of a synthesis. We have 2 reactants, magnesium and oxygen, that we're going to combine to make one single product. So it's the Mg and the O are going to stick together to make one compound. But the problem is you can't just smoosh them together directly. You need to use the charges that these atoms will form when they gain or lose electrons during bonding. So like magnesium's over here, it's got 2 valence electrons. It's going to ditch them when it bonds with oxygen. So it's going to form ions with +2 charges. Oxygen's over here. It's got 6 valence electrons. It's going to gain 2 when it bonds to become stable. So it's Plus 2 and minus 2, they directly cancel out to 0. So you would just need 1 magnesium per 1 oxygen to make a neutral compound. Or you do that cross down trick that I taught you in class. You would get 2 to 2, which you would then need to remember to simplify down to 1 to 1. So it's just MgO for the product of the synthesis reaction, which is magnesium oxide. All right, we are always going to show a conservation of atoms when we write chemical equations. We're always going to show that we don't create or destroy atoms over the course of a chemical reaction. So we started with 2 oxygens here on the left. We only have 1 on the right. So to fix that, we can use a coefficient of 2 in front of our magnesium oxide. That 2 doubles the O's up, so they're the same on both sides, but it also doubles the magnesium, which is why we also need a coefficient of 2 in front of magnesium. You can either leave it blank or put a 1 in front of the O2. All right, that's something I taught you already. That's a synthesis reaction. That's a binary, 2 elements combining to make 1 compound. I taught you decomposition with synthesis because basically it's the reverse. You have 1 substance that decomposes or breaks down into 2 or more simpler products. So like you could have water, a compound that breaks down into the elements that compose it. And those are the types of decomposition reactions we will be working with. There are more complex ones in which a compound breaks down into simpler compounds. But basically, all decomposition are going to follow that one thing, breaking down into 2 things format. Okay, so here's an example decomposition. We have sodium fluoride as our reactant. It's going to break down into the elements which compose it, which are sodium and fluorine. But we have to be careful here. Fluorine is the fear in never have fear of ice cold bears. It's diatomic. So it's never just F, it's always F2. So that means to balance this, to show a conservation of atoms, we're not creating or destroying any, I need a coefficient of 2 in front of the NaF. It'll double the F's, but also the sodiums, which is why I also need a coefficient of 2 in front of my Na. I can put a 1 in front of my F2. It's not required though, because coefficients of 1 typically do not appear in reaction equations. Okay, one new thing for today, and then you're going to practice this. The one new thing is what a combustion reaction is and what the products of all combustion reactions are. The hardest part about this is just going to be balancing these things. Combustion reactions are kind of tricky to balance. So what is combustion? When something's burning, it's on fire, it is combusting. So combustion reactions are the fire reactions. They release a lot of energy as the reaction occurs. So there's really 2 types of combustion reactions. There's incomplete and complete combustion. I will be teaching you about complete combustion. But what's the difference? So like when we light the Bunsen burner in the back of the lab, I always tell you to adjust the air intake openings so that the flame turns blue with a lighter blue inner cone. The reason why I'm telling you to do that is you're adjusting the amount of oxygen that's entering the burner so that all the gas, the methane gas that we're combusting or going to react is going to combust. It's going to burn up. If the flame which looks orange, what that means is incomplete combustion's occurring. We're combusting the methane, we're reacting the methane, but we don't have enough oxygen to react at all because fire needs oxygen to burn, right? So in incomplete combustion, when the flame looks orange, the reason why is there's not enough oxygen present to react all of what you're combusting. In this case, it's the methane. When we open those air intake openings on the base of the burner a little bit further, we let a little more O2 in there. Now we have enough oxygen to react all the gas that we are combusting. The flame turns blue. It is complete combustion. So basically, here's the deal. All the combustion reactions you're going to see are basically going to look the same. They are all going to have O2, oxygen, as a reactant. Fire needs oxygen to burn. We are going to assume complete combustion always. And if we can assume complete combustion, the flame is blue, there's 2 products, and they're exactly the same every time, carbon dioxide and water. There's products of incomplete combustion besides those. Don't worry about it. We're talking about complete. So basically all combustion reactions have those parts in common. O2 on the left, carbon dioxide and water on the right. The only thing that's going to differ is the identity of the hydrocarbon. What's a hydrocarbon? CnHn. It's any combination of carbon and hydrogen. They're the fuel for the combustion reaction, like propane, methane, butane, fuel to light on fire and combust. Aside from the identity of the hydrocarbon, how many carbons and hydrogens are in what you're combusting, the rest of the reaction equation should be exactly the same. It's the balancing that's going to be a pain in the butt. Okay, we are going to complete these reaction equations. We're going to classify them. What kind of reaction is it? Synthesis, decomposition, combustion. And then we're going to balance them to show a conservation of atoms, that we're not creating or destroying any atoms over the course of any chemical reaction ever. All right, number one, let's check it out. We've got C2H6. Ooh, that's a hydrocarbon, a combination of carbon and hydrogen only. And it's reacting with oxygen. Hydrocarbons are great fuel sources. They burn or combust easily in the presence of oxygen. So I'm going to go ahead and call reaction number one a combustion. And how I know is I see a hydrocarbon, pure carbon and pure hydrogen bonded together, and I see oxygen as the other reactant. Now, as soon as I identify its combustion, that means the reaction products are always carbon dioxide and water. We're always going to assume complete combustion. So those products are always the same. It's the balancing that could be a pain in the butt. So now just bear with me here, because we're going to have to change some stuff. Let me see if I can, whoopsies, did not mean to do that. All right, so I guess I have one thickness of pen to work with. All right, I'll start with red. All right, so you look over here on the left, there's 2 carbons. There's only 1 carbon on the right. So we'll put a coefficient of 2 here to balance the carbons. All right, we can fix the hydrogens momentarily. There's 6 here, but only 2 here. So yeah, I can put a coefficient of 3 there, and that's going to give me 6 hydrogens. But it's going to make the O's pretty much impossible to balance using a whole number coefficient. Why? Now there's 3 O's here in total, 3 times the 1, and now there's 4 O's here. So that's 7 O's, and no whole number times 2 is going to give me 7. So the trick that I've taught some of us in class is this. When you get an odd number of an element, like this 3 here is giving me an odd number of oxygens, 3 O's, double that coefficient, so 3 times 2 is 6, and then work it back through. So now I have 6 times 2, 12 hydrogens on the right. So I can make 12 hydrogens here by putting a coefficient of 2. Okay. But that 2 also doubles the carbons. I had 2 times 2. Now I have 4. So that becomes a 4. So we got 4 carbons on the left and right. Now retotal the O's. 4 times the 2, there's 8 O's here. 6 times the 1, there's now 6 O's here. So 8 and 6 makes 14 total. I can finish balancing this with a coefficient of 7 in front of the O2 to make 14 oxygens in total be present on both sides of the equation. So be careful with the combustion. They're tricky because oxygen is in both of the products, in the carbon dioxide and the water. You're going to have to play with it in order to balance the whole thing out. Okay, moving on. Number 2, I see 2 individual reactants. 2 elements reacting, lithium and oxygen. What's going to happen is they're going to combine to make a single product. And that is called a synthesis reaction. So we're going to combine lithium and oxygen together, but we're not just going to put Li and 2 O's, just smoosh them. We have to figure out the charges these elements, atoms of these elements would form during the bonding process. So hopefully by now, this is something you can do. Lithium's in group 1, It's going to lose its 1 valence electron and form an ion with a +1 charge. Oxygen's in group 16. It's going to gain 2 electrons. It has 6 valence. Needs to gain 2 to get to 8. It's going to be -2. Either do the cross down trick or use logic. Either way you do it, you're going to end up with 2 lithiums per every 1 oxygen. Now you've got to balance it to show a conservation of atoms. There's 1 lithium on the left and 2 on the right. So I can put a coefficient of 2 here to fix that. There's 2 O's on the left and only 1 on the right. Oh, shoot. We'll put a 2 there to give 2 O's on both sides. But now there's 2 times 2, 4 lithiums in total on the left side of the equation. So we'd have to fix this coefficient up to a 4. Either leave it blank or put a 1 in the coefficient in front of the O2. Okay, number 3, I see just one single reactant, the compound NABR. If I just see one reactant, it's going to break down. It's going to decompose into the elements that make it up in a you know me and my spelling, decomposition reaction. Okay, so NABR is going to break down into Na and Br. It's going to decompose, but never have fear of ice cold bears. Bromine is diatomic. So it's never just Br, it's always Br2 in nature. Okay, this one's not too bad to balance. There's 1 bromine on the left, 2 on the right, so I can throw a coefficient of 2 here. That also doubles my sodiums, so I need a coefficient of 2 there. Either leave it blank or put a 1 in front of the Br2. Okay, I'd say that's like maybe level 1. Level 2, what we're going to work towards, and this is going to get harder when I introduce the last 2 reaction classification types, is going from this, like a reaction description, to writing the actual reaction equation. So let's give it a go. We're going to write the whole thing, reactants and products, and then we're going to balance to show that conservation of atoms. Okay, we have number 1, the combining of potassium and sulfur through a synthesis reaction. Okay, so it's synthesis. Our reactants, we're combining our potassium and sulfur. So potassium's element symbol is K. It's not diatomic. Plus sulfur, whose element symbol is S. Also not diatomic. But I can't just assume there's 1 K per 1 S. I need to use the charges atoms of these elements form when they go through the bonding process. So K is in group 1. It has 1 valence electron. It loses it to form a K plus 1 ion during bonding. Sulfur is in group 16 with oxygen. It's got 6 valence. It needs to gain 2 more to achieve stability during bonding. Use the cross-down trick or logic. Either way you do it, you need 2 potassiums per every 1 sulfur in the final formula for this product, which is potassium sulfide. Got to balance it. Got to show that conservation of atoms. I'll put a 2 in front of the K. So there's 2 Ks on both sides and 1 S on both sides. All right, number 2, the combustion of propane, which they told us was C3H8. All combustion reactions have the exact same format. There's some hydrocarbon, which they gave us, and it's the fuel for the fire. It's going to burn. That's what combustion is. In order for it to burn, what really means is it's got to react with O2, atmospheric oxygen. Now, those 2 are going to react, and as long as we assume complete combustion, which we always will, the same 2 products are formed, carbon dioxide and water. So you just need to memorize that combustion always makes CO2 and water, and the other reactant, aside from the hydrocarbon that you're given, has got to be oxygen, because it's going to burn up in the presence of O2. These are the ones that can be a bear to balance. This one's actually not awful. There's 3 carbons on the left, so I can throw a 3 here. There's 8 hydrogens on the left. I can throw a 4 here to make 8 hydrogens also on the right. If I total it up, 3 times 2, there's 6 oxygens here from the 3 carbon dioxides. 4 times 1, there's 4 oxygens from the 4 water molecules. So a total of 10. What number times 2 makes 10? 5 times 2 makes 10. There are now 10 total oxygens on both sides of the reaction equation. Okay, one more. Okay, the decomposition of aluminum oxide. All decomposition reactions have a 1 to 2 format. The compound you're provided with is going to break down into the elements that compose it. We're going to do binary decompositions. There's more complicated ones, but we'll stick with binary. So our one reactant is aluminum oxide. We have to figure out its formula. Aluminum has 3 valence electrons. When it bonds, it loses all 3 to achieve stability. Oxygen has 6 valence. When it bonds, it gains 2 to get to the 8 stable outermost electrons. So either logic or the cross down trick, the actual formula for aluminum oxide is Al2O3. And it's going to decompose or break down into the elements that make it up, which are aluminum and oxygen. Never have fear of ice cold bears. Of is oxygen. It's diatomic, O2. So to balance this, we got to get everything sorted. There are 2 oxygens on the right and 3 on the left. So you go like, what's the least common multiple of 2 and 3, which is 6. So I'll make 6 on both sides by putting a 2 here and a 3 here. To fix the aluminums, I now have 2 times 2, 4 on the left. So I'll put a coefficient of 4 on the right to balance it out. Okay, now you're going to practice this. I have a paper practice and a paper answer key you're going to be working with today. Understand that when I come back on Thursday, this is going to go up a level, like significantly. So you need to make sure you understand this and master this today while things are still easier. Mr. Nagel can help you, ask questions, and don't be afraid to look at the answer key for help if you get stuck. That's why I make the key. It's not cheating to look at the key if you're using it for support. All right, I miss you guys. Trust me, I would definitely rather be in the classroom teaching you right now. I'll see you again on Thursday. Bye-bye.